Good afternoon, everyone. I am very, very happy to be here. I would like to thank Dario and Analu at Amata and everybody at Amata for inviting me here. I've only been here 2.5 days, but I have already met so many people who are so friendly and so nice, and many of them who are also very knowledgeable about wood, but also very passionate about wood and have a vision about wood. And from what I have already seen, I think that Brazil is ready to have an explosion in timber construction. I think it's something that a lot of people are ready to do. And anyway, I hope that you enjoy my presentation today. Wood, of course, has been used for a very long time and may very well be the very first construction material that people have used. And many of the buildings that were built centuries ago are still standing today. Wood at the time was used in construction, important construction such as churches and temples. But at the turn of the century, with the Industrial Revolution, reinforced concrete and later structural steel took over in the construction of important structures, and still today, unfortunately, is still viewed as the preferred, are still viewed as the preferred materials for the construction of large commercial structures. 2 or 3 years ago, we were asked to do a small project, a research project, which I would have thought even 5 years ago was impossible. We were hired by a Finnish company to redesign. I will let you watch. So, Metsä Wood, which is a Finnish timber company, wanted to show that it was possible to do almost anything in wood. So they asked some engineers and architects first to redesign the Colosseum in Rome, and then to redesign the Empire State Building to show that from a technical point of view, wood could be used to build almost anything. So we actually developed a construction model and analyzed it on the computer, and actually found that it was in fact possible to build the Empire State Building out of laminated veneer lumber. So what you see here are pre-stressed tendons running through a hollow beam, creating a moment frame in the short direction, and then in the long direction on either side of the elevator core we have very large solid timber elements, timber shear walls, 75 meters long, that provide the lateral rigidity for the building. So if we were to build the Empire State today, maybe it would look like this. And so what brought us to this point? What made it possible for us to consider doing something like this? And as I said, even 5 years ago, I don't think I would have taken this project seriously. But in the last 20 years, when I started my career as an engineer, a lot of buildings in Canada were still built with chainsaws. But over the last 20 years, a few things happened in the timber industry that completely changed what was possible. That includes software and CNC fabrication, state-of-the-art connections, and the latest significant advancement in timber engineering, mass timber construction. An engineer by the name of Julius Natterer in Switzerland about 20 years ago decided that it was time to develop cutting robots, CNC machines, that could fabricate large timber elements. And of course, to drive those CNC robots, you need to develop software. So this is a model using the software CADWork, which is really designed to translate images into robot codes. And that made it possible to then develop machines like this one. This is a 5-axis gantry machine, which can work on very, very large timber elements. And these machines have an accuracy of 0.1 to 0.3 millimeters, depending on the type of cut that you do. So as an engineer, this type of manufacturing capability had a very big impact on how we were able to design timber structures, but also made it possible to develop connection systems that were much, much more efficient than the old connection systems that we were used to 20 years ago. So a cutting robot like this can fabricate a piece of wood in almost any shape you want with very high accuracies. Using this manufacturing capability, one of the earlier projects that we did with Michael Green was the Prince George Airport. It's a small regional airport. And because of the scale of the building, we didn't want to do something excessively elaborate structurally. We decided to do a very simple post and beam structure, but focusing on the quality of the details, using the new manufacturing capabilities that we had. So this is the corridor that joins the original building, which was a steel building, to the new expansion, which is made out of wood. And one of the innovative connectors that we used in wood are steel castings. Castings are really useful when you're trying to do large number of identical connections and where you want to have an architectural expression. So they become quite economical if you make hundreds of them. In this case, we needed 525 or so of these connectors. And we used them to support the roof structure because we wanted to hide some surfaces above the beams, but also to make the wood, the roof plane appear to float above the beams. We also use the same connectors to support the glass and connect them to the column. And you will notice that the column is shaped in an elliptical shape using the 5-axis machine that I showed you before. And since we had the mold for the castings, might as well use them to make benches. So that was an early project where we started to experiment with the manufacturing capabilities that were available to us, as well as some of the new connection systems that allowed us to use. So this is a view again from the outside. Another airport, this time in the United States, in North Carolina, a much bigger one. This project is a 1 million square foot building, so 100,000 square meters, more or less. And it has a roof that is made from a combination of steel and glulam. And some of the connections have very, very large forces. This particular one was designed for a tension load of about 250,000 kilograms, so 250 tons. And so we were able to design these connections very economically using a proprietary connector from Germany, designed by an engineer named Peter Birchie, who unfortunately passed away about 2 years ago. But this connection was originally designed with gluten rods, and by introducing this new modern connector, we were able to save $1.5 million on the cost of the connections on a $7 million contract. So this is a view of the connection. And I think if you consider the amount of load that this connection carries, it's quite discreet and quite simple looking. This is a project by Shigeru Ban and an engineer, a Swiss engineer by the name of Hermann Blumer, whom I consider probably to be the best engineer, a timber engineer in the world right now. This is an older shell that they did together, and what I want to show you here is that the solution for the shell basically involves the use of planks which are bent and lapped together to create a shell structure. Because the planks can only be bent in one direction, the trajectory of the timber elements are limited, but the connections are very simple. One of the later shells that he did using 3D modeling and CNC fabrication is a shell that was used for a golf house in Korea, the Nine River Golf House. And you will see here double curvature glulam, which are highly CNC manufactured, and this allowed the designers to achieve a structure that was really quite beautiful. I think probably one of the most complex and beautiful timber structures in the world right now. So the last really significant advent in timber engineering is the invention of solid wood construction, or the concept of solid wood construction. Centuries ago, of course, we used post and beam. In the 40s and 60s, or 40s and 50s, in North America in particular, light frame construction became very popular and essentially took over the residential market. And about 20 years ago, a forester by the name of Wolfgang Weyer from Austria thought that he needed to develop a material that could replace stone and masonry in residential construction in Austria. He knew that the Austrian homeowner wanted a very robust material. They were not interested in building their houses with light frame. And so he decided to create a large timber panel that maybe he could sell to homeowners. But what's important to me is not so much the invention of CLT, but the concept of solid wood panel construction. It's the construction system that is important here. And you can really find different types of solid wood panels. In North America, we have been manufacturing LSL and LVL for a very long time, and these products, before they are cut up into small pieces, are manufactured in very large sheets of 2.4 meters by 19 meters. But their thickness is limited. You can buy these panels with a maximum thickness of about 90 millimeters. CLT, of course, can be manufactured with much larger dimensions, with thicknesses as high as 30 centimeters, with widths of 3.5 meters and lengths of also 19 meters. Now, originally, I had a little bit of a hard time justifying using so much wood in a building. But eventually, I wrapped my head around the fact that, well, you can use large masses of a material that emits carbon and is very heavy and not that great for the environment. Or you can use a renewable material that is very energy efficient, very light, and much better for the environment. And because wood is so much lighter, it tends to be thinner, so it is efficient in many, many ways. We discovered solid wood panel construction in 2007 at a time when CLT was not available in North America, but we wanted to experiment with solid wood construction right away. This is a project that I did again with Michael Green in 2009. This structure in the middle here connects two existing concrete buildings. And is made with glulam columns, and then a panel system that we developed using LSL panels, which were too thin to span the 10 meters across the width of the corridor. So we decided to laminate them together in the same way that CLT is laminated together, but leaving some spaces in the middle of the panel to integrate services. So here you have a view of the panels, which is glued and screwed together. And you see here the voids that we left in the middle to integrate services. And here is a panel, which is prefabricated in the shop with dimensions of 10 meters by 3.6 meters, and then installed on site very quickly. We normally don't think of LSL as an architectural material, but if you sand it with a medium sand and put a sealer on it, I think it looks really quite attractive. So this is a view of the completed link structure or corridor structure. Michael also used LSL as a sealing material, so for non-structural sealing material throughout the building. And this is a view of the corridor from the roof garden. Another project where we experimented with solid wood panels and was quite pivotal in our research and our experiments in mass wood construction. This is the Earth Science building at the University of British Columbia. This project was chosen by the province of British Columbia as a demonstration project at the time. So we had a little bit of funding to experiment with innovative structures. So what you see here is a regular cast-in-place concrete wing. And the reason for that is that the laboratory in the basement has a rock crusher, which creates a lot of vibration. And the university was really nervous about the idea of doing a wood structure where vibration might be an issue. But they agreed to do the office building and the central atrium in wood. And we have a very large canopy that wraps around the building, which we designed in CLT, hoping that we would get CLT in time. But we knew that we wouldn't get the CLT panels from Canadian manufacturers in time for the floor structure. So we decided to use LSL again. But because the spans were quite large, we had to also use the concrete topping in a composite structure. The connector, there are many connectors that you can use to do wood concrete composite. The one that we prefer is this one. It's the HBV connector, which was developed in Germany. So very simply, you run a saw cut through the panel, you put some glue in the saw cut, and then you push the mesh into it. We add a layer of insulation to get an acoustic separation, because the intention is to leave the structure exposed. So we need to develop an acoustic separation within the structure itself. And with the concrete poured, this is what it looks like. This is a sample that we tested in the laboratory at UBC, the FP Innovation Laboratory. And you can see here how the concrete layer is already sliding quite a lot on top of the wood structure. So the connector, which is connecting the two layers together, is already yielding almost 25 millimeters, which shows that it has a huge amount of ductility. This panel here started to fail with the equivalent of 4 feet of water in load. So very robust, very ductile, and very reliable. The contractor on this particular project decided to install all of these elements on site. I think if they had chosen to prefabricate, they would have saved a lot of time on site. And it rains in Vancouver as much, if not more, than it rains here in Sao Paulo, so that would have been a good idea. But here you see the floor with all the connectors, the insulation, and the reinforcing in place, ready for the pour. Structurelam product managed to get their production facility just in time to supply panels to this project. So this is the first project that Structurelam product supplied. So we were able to build a roof with CLT panels. You will notice here that we put a membrane in the shop to protect the panel from the rain. And if you want, you can also seal the joints between the panels on site as you go and keep the surface watertight. And the canopy, which was also built out of CLT, is now in place. We have a wood beam which is on top of the columns, so the CLT panels are actually hung from the top with the beams being completely invisible. But the biggest innovation in the project, I think, was the central staircase. The architects wanted an architectural element that was quite impressive, and the atrium, of course, was the perfect place to do it. So we designed a fully cantilevered staircase. So this staircase is not hung from the roof, it's not connected to the columns, it's actually cantilevered from the floors. The blue elements that you see there is steel. The beige elements is glulam on the flat. And this is what the connections look like. So again, we use a perforated steel plate, which is glued into the wood and provides very rigid and very strong connections. The steel plate, which goes across the landing, is there to reinforce the glulam in the weak direction, because glulam, unlike CLT, is strong only in one direction, but also acts as a shear reinforcing to keep the landing from failing in shear. So you see here the landing, which is flown in. So part of the structure was glued in the shop, and the other half had to be glued on site. So you see here, they're preparing the element for gluing. So they're just sealing the bottom of the element to keep the glue from leaking. And this is where you really need the CNC fabrication. So when this happened, we were all praying that this thing would fit. And this is what it looked like before it was glued. So that's the beauty of CNC fabrication. Once the elements were put together, we have to finish the connection by gluing the second half on site. And this is done with a compressed glue gun very quickly. So this is a view, again, of the canopy from the inside, and the finished stair with all the finishes on. When the stair was finished, I was standing at the top looking at it before the guardrails were on, and I thought, oh my God, what have we done? The students are never going to want to walk on this thing. It looked really quite scary. The architect very intentionally made the building look modern. So this is a recognition of the fact that wood is now a modern, high-tech material. So the architecture doesn't shy away from using that concept. This is a view of the timber wing from the back of the building. Another project that was very important in our experimentation was the Ronald McDonald House in Vancouver. I think many of you must know that Ronald McDonald is an organization that provides housing for families of sick children who can't afford a hotel. So this is the second or fourth largest Ronald McDonald House around the world, from all the Ronald McDonald House around the world. Again, with Michael Green. Michael really wanted the project or the building to feel, to not feel like an institution, but rather to feel like a home. So we broke up the project into 4 houses, 4-story houses, and we were mandated to design the building for a 100-year life. So Michael chose brick as a cladding system. Now, brick can be mounted on light frame, but light frame is quite flexible, moves quite a lot, and when brick moves, it cracks and then becomes susceptible to water infiltration and a shorter life. So we chose to use CLT as a support for the brick. So all the walls are made out of CLT. But we we still chose to use light frame for the floor structure so that we could incorporate services easily, but also to save cost. And in North America, there's a system in concrete called tilt-up, which is used quite a lot. So we had the idea of using CLT tilt-up walls, and we promised the contractor that they would save lots of time on site. We had never done it, but we made the promise anyway. And so after, this is a view of the floor section and wall section. So after the first house, we were 2 months behind schedule. So people were not very pleased with us. But once the contractor got the hang of it, once they became used to how this worked, they became a lot faster, and at the end of the project actually saved 2 months in the original schedule. So you see here the CLT in place with the membrane and the brick finish. And then a few pictures of the finished building. The residential areas were covered with gypsum wallboard because we were using a very thin CLT and couldn't rely on it for fire protection. But the common areas had CLT exposed. And the stairs also were made out of CLT. So you see here the stair for the big people and the stair for the small people next to it. Another innovative project we did with CLT, a very small one. This was a design-build competition. One of the donors for the project owned an aircraft maintenance company, and the only request he had was that we make the building relate to his business somehow. So we suggested shaping the building like an airfoil. When I was a little kid, I used to play with model airplanes a lot. I would crash them, and if you crash them often enough, eventually you have to rebuild them from scratch. So you buy sheets of balsa wood, and then you use the little paper shapes to cut new pieces. So we had the idea of cutting CLT shapes out of sheets of CLT to create those organic forms. And typically, airplane wings are made with very, very light elements, which are braced at very, very tight spacing to keep them from buckling. So we developed a structure that consisted of a moment frame in one direction using CLT shapes, and then braced them at very tight spacing at 3 meters on center in the other direction. And that created this structure here. So the moment frame is running in this direction with a span of 12 meters, and then braced with bridging elements in the other direction, and then we put the sprinkler lines on top to hide it. So this is a fitness center, and then viewed from the outside. I want to talk a little bit about prefabrication, because timber construction is really most efficient when it's fully prefabricated. Actually, this is one of its advantages. You can achieve a lot of speed on site and also cover up the structure a lot more quickly if you prefabricate and protect it from the elements. This is actually our own shop, which we built 4 years ago, where we manufacture light frame panels which are pre-insulated in the shop to the Passive House standards, so very energy efficient envelope systems. And this factory that you see here, which is 1,500 square meters, was prefabricated on a different site and then erected in 8 days. Prefabrication can be very useful if you have a very short construction schedule, or if you're building in an area that has a very short construction schedule because of weather, because of winter. In this case, this is a museum in Whistler, where snow starts to fall in October. and doesn't melt before April. So if you don't finish the roof before the snow comes, it's quite common in Whistler that the site just shuts down and everybody waits for the spring to work again. So we propose using prefabricated wood panels on this steel structure. You see the panels here, which were fabricated in the shop that I just showed you. Again, you install the membrane in the factory so that you can waterproof the roof very, very quickly. And prefabrication also allows you to achieve much better tolerance or much better accuracy, as you can see here. And here are some shots of the finished building again. This particular wood structure here is architectural. And then viewed from the staircase below, this is a project by Patcow Architects, who are very well-known Canadian architects. And the reason that the building is elevated from the ground is that the building is in a floodplain. So there's a possibility that we get 2 meters of water flowing under the building when the creek overflows. A few shots from the inside. The structure in this case is covered up. Another project by the same architect to demonstrate how solid wood construction can be a lot faster, how prefabrication in solid wood construction can be a lot faster. We started this project in 2007 before CLT became available, and we actually tried to convince the owner and the architect to use CLT, even if it would have to be imported, because this is the kind of shape that can so efficiently be done with CLT. Unfortunately, the owner didn't want to import panels from Europe at the time and didn't really, I think, understand the potential cost savings that would be achieved. So we framed the building the normal way, by hand, on site, piece by piece. And because it is such a complex shape, it took 18 months to complete the structure to the level of accuracy that the architect wanted. This is a view of the interior of the building. And then a view from the exterior. In parallel, we were designing another house, not quite as complex from a geometric point of view, but about the same size. And every one of those panels is different, so it's not like there's a lot of repetition here. And in this case, the architect was the owner of the house, and we managed to convince him that it was worthwhile importing CLT from Europe to build this house. So there was a lot of work that was done up front, coordinating the deliveries, coordinating all the shop drawings. But when the material arrived from Austria in containers, it took just 6 days to erect the structure. So the first building I showed you took 18 months. This one took 6 days. This was the first CLT building in North America. You see here, even the electrical outlets are all CNC manufactured in the shop. A few images from the building, from the outside. So we went through about a decade of experimentation with CNC fabrication, new connectors, solid wood panels. And then Michael decided that it was time to grow up and suggested that we do a study to prove that we could build high-rises with timber. So we applied for a small grant and proposed to design a 12-story building out of CLT. This was not the first time that somebody had the idea to do that. As a matter of fact, in 2009, Andrew Waugh built the first mid-rise in CLT in London. It was 8 stories on top of a concrete podium, so a 9-story building, entirely built out of CLT. But the conversation in North America hadn't really started yet about this. So when we issued our report, again with the idea that we would analyze a 12-story building. We did a bit of work, and then Michael went to Japan with his son and visited this temple, which is about 1,300, 1,400 years old, and almost the height of a 12-story building. So Michael came back and said, well, we can't do a 12-story building. They did it in Japan, 1,500 years ago. So we got to do 20 stories. Now, this is very easy for an architect to say. We're going to do 20 stories. I drove around Vancouver for weeks, looking at buildings and counting the balconies and thinking 20 stories is really scary. But we developed some concepts, put them in the computer, modeled them, and this one in particular, with the moment frames on the perimeter, worked really, really well. So I told Michael, I said, you know what, I think we can go 30 stories. So he went to a conference in Australia and was interviewed by a journalist after his speech, after his talk, and mentioned that he thought we could go 30 stories. And then the next day, it was in the Vancouver Sun. They were announcing that we were building a 30-story building in BC. So now I was stuck having to design a 30-story prototype. But this particular system with the perimeter moment frame actually worked really well. So that's what we published. And then a company in Chicago that is very well known for their design of high-rises. As a matter of fact, they've designed many of the tallest buildings in the world over the years, SOM, redesigned one of their concrete buildings, which was 42 stories tall, and said that they could do it in wood. So we didn't look that crazy anymore. But still, there were a lot of blogs on the internet when these reports came out claiming that the idea of building wood high-rises was just crazy. And so that brings us to the wood myths that are really everywhere in the world, including Canada, where we've been working with wood for so long. But everybody has the same fears or the same misconceptions about wood. The first one is that wood is weak. Engineered wood is about 3 times stronger than regular sawn timber, more or less. And there are engineered woods out there that are as strong as reinforced concrete. But you need to keep in mind, of course, that wood is a quarter of the weight. So a building that is built out of wood, including all the finishes, will be about half as heavy as a concrete building, and the material is just as strong as concrete. So from a structural point of view, there's really no barrier here. In fact, a tree in its original form is a cantilever with a great big sail on it. And we have trees that are, in Canada, in BC, we have trees that are 33 stories tall and have stood for centuries. In the United States, they have some that are even taller. In contrast, today, the tallest building we can build in wood in British Columbia is 6 stories. We need special permissions to build anything taller. But I think everybody around the world is now realizing that these limitations are not really founded on the reality that we have today. We design stadiums out of engineered wood with spans of 70, 75 meters. Everybody, of course, worries about the fact that wood burns. Well, it does burn, but it burns in a way that we understand very well, in a very controlled manner, and we can engineer for it. We have also to understand the difference between combustible materials and fire-resistant materials. Wood is combustible, but it is fire-resistant. When wood burns, there is a char layer that develops on the surface that protects the inner layer from high heat, and it burns very slowly at a rate of 0.6 to 0.7 millimeters per minute. So in 2 hours, you will lose 88 millimeters. The structure that is left behind is perfectly capable of carrying load, unlike steel that completely loses its strength. But more importantly, panels of this type are airtight because they're a glued product, so they can stop smoke and heat from migrating into the space that is adjacent to it. So if you build a building out of CLT, and make sure that all your joints are airtight, you can contain a fire for many hours and protect the rest of the building from fire spread or even from heat damage, because some of these panels were tested in Ottawa, 10 centimeter panel. After 2 hours of intense heat, you could still put your hand on the opposite side of it and not burn your hand. So the key thing to understand here is that not all wood systems are equal when it comes to fire performance. When you start a fire, you start it with small kindlings, because you can easily light a small piece of wood on fire. You don't start with a log, because it's very difficult to light a log from scratch. Now imagine a big solid wood panel, even more difficult. And the code people around the world are understanding that they cannot treat the different timber systems the same way. And the Canadian code, in any case, is being rewritten to eliminate this business of combustible versus non-combustible construction, and will be based very soon on performance alone. So this is actually a picture of a light frame building that was built in BC. This was the first 6-story building, and unfortunately, somebody was careless during construction. The building caught on fire, the light frame burnt very quickly, but the elevator shaft, which was built out of solid wood, remained standing after the fire. Wood rots. Well, it rots if it gets wet. If you protect it with a good envelope and you design it properly, you make sure that you keep the wood from absorbing moisture or getting wet from direct exposure, it can last centuries. And there are many, many buildings around the world that prove that demonstrate that. Of course, it is susceptible to termites, but again, we know how to protect the wood from that. And research is ongoing now to develop better and better products every year. There's a product in the US called Cup Coat that apparently can be applied without pressure treatment, just a topical application, and is actually very effective at resisting termites. There were a lot of environmentally concerned citizens that made comments about the fact that if we start building high rises out of wood, we're going to shave the planet clean. Well, the truth is that with responsible forest management, what we have is not deforestation, it's forestry. And forestry in itself is a good thing. By giving value to the wood, you ensure that the forests are replenished. If you don't give value to the wood, people cut it down and they leave the ground bare. So the problem is not forestry, the problem is deforestation. We need to understand the difference. And we need to replant our forest. In Canada, we only use a fraction of a % of the available forest cover every year, and we're the largest softwood timber supplier in the world. Wood is expensive. Well, more and more that is not true. Now that we are developing more efficient connection systems, more efficient manufacturing, and steel to construction in particular, now that contractors are understanding how to put these projects together, now that engineers and architects learn more and more about how to design them, we are finding that wood is actually becoming very competitive with concrete. It became more competitive, it became competitive with concrete in London over the last 2 or 3 years, and we're finding in Vancouver, BC now, that this is also the case. For the very first time, we designed a project that was done in concrete and in wood, and the wood actually came in cheaper just a few months ago in Vancouver. Now, why is this so important? Well, the world is going to become 70% urban by 2050. That means that we're going to build 3 billion new residential units by 2050. And most of these units are going to be built in countries where concrete is prevalent. The concrete industry, as it is responsible for 8% of the carbon footprint on the planet, which is more than all the transportation industries combined. And if we build 3 billion concrete units by 2050, that footprint is going to go way up. Now, that's not the solution. That's not what we're trying to do. Wood, in contrast, is renewable. You plant a seed, it grows. And as it grows, it absorbs carbon. About a ton of carbon per cubic meter, more or less. Concrete, in contrast, produces a ton of carbon per cubic meter. And wood grows with the sun. It's the only construction material that is grown by the sun, naturally. So for these reasons, following all the negative blogs that came out, the media realized that there was something going on here that was really quite exciting. And we started to see articles like this one, Popular Science claiming that wood had become the most advanced material in the world, the most advanced building material in the world. So following this study, the province of BC sponsored the construction of a tall wood building. How am I doing for time here? Am I doing okay for time? So the province actually sponsored the construction of this building. Officially, we couldn't call it an 8-story building, but it is in fact an 8-story building. And the condition was that we do a peer review on the design of this building, both for structure and for fire engineering. So we were given a special permission with the peer review to build this building. It's entirely made out of wood. So we're not even using concrete topping here except in the mechanical room for sound control. And we wanted to expose as much of the wood as we could. So we developed a strategy to hide all the services in the floor system. So we used a thicker CLT on the bottom and then a thinner one on the top, which we connected together. And that gave us a corrugated floor section that gave us the opportunity to hide the services. All good mass wood projects start with a good model to drive the CNC fabrication. And this project was actually designed and built in 16 months through the winter. Unlike concrete, you don't have to heat wood to be able to work with it. And mass timber sites, in contrast with steel construction and concrete construction, is very quiet, clean, and safe. You can work with very simple tools, and most of the work is either done in the factory or on the ground. So you install all the connectors on the ground and then lift the panels for installation. These panels are mostly connected with very simple self-tapping screws, which are a really high-tech connector. It's like an old screw that you might be used to, but with very high-strength steel. And the design of these screws make it possible to install them without drilling very easily. So this is our finished building. So this was, again, to demonstrate the use of wood. So you have LVL for the canopy, you have LVL for the support of the glass, because we want a product that's very stable dimensionally to attach the glass to. You have glue lamp posts and beams, CLT. The wood that is exposed to the outside here is Alaskan yellow cedar, which ages very well in the weather. This is a view from the interior with the removable panels for the services. And the upper 3 floors didn't have a tenant at the time we built the building, so they were left empty for a tenant to finish. The facade is made out of a combination of natural cedar and charred cedar. And the reason for the char is that we needed to develop a facade that had a flame rating that was low enough to control the flame on the facade. And so we did a bunch of tests with different charring depths to achieve the flame spread rating that we needed. So as you can see here, it's the charring is quite deep. Okay, so there's another view of the building. So looking into the future, but also looking at how mass timber construction will do in the market. This is a developer project in Melbourne, Australia that I believe was sold out in a matter of a day. And this was developed by a developer, so it's a cost-driven project. Another one in Norway, a 14-story building, which was completed a couple of years ago. This is a project that was done at UBC in Vancouver. It is right now the tallest wood building in the world at 17 stories. We didn't design this one. This was done by one of our competitors. And it has a concrete core, and in this case, all the wood is covered up with drywall. But it's a first step. We also designed a building, the first tall wood building in China, which will be completed this year. A 9-story building. And we're currently working with Shigeru Ban to design this tower. This is 14 stories of concrete and 8 stories of wood at the top. This building is actually adjacent to a famous building by Arthur Erickson, which is 14 stories tall. So the concrete construction matches the concrete building that Erickson did. And then there is a wood lantern at the top that extends into the sky. In 2 weeks, we go to Bordeaux to see if we were successful with a number of competitions. We entered a competition to design 3 17-story all-wood buildings. So the cores, the gravity structure, all made out of wood with Michael Green. And we also have an 80-meter tower with a concrete core with Shigeru Ban, with Kengo Kuma. So 80 meters is about 30 stories, 28, 30 stories. So we will find out in 2 weeks if we were successful with this. So as an engineer, I have had in my career the opportunity to work with amazing architects who have an appreciation for the relationship between structure and architecture, and who've given me the chance to do more than just number crunching. But Le Corbusier seemed to think that engineers should just be number crunchers. Arup disagreed with that and was able actually to push his weight around quite a bit from what we see. And in Vancouver, whenever we want to get what we want and the architect doesn't want to give it to us, we say, well, it's required by because of seismic loads. And seismic loads are nebulous enough that the architect will usually agree. Peter Rice, who was one of the most brilliant engineers of the last century and is remembered as being a very creative engineer, actually started his career as a very pragmatic designer. He was somewhat of a mathematical genius, and the first 10 years of his career were really focused on engineering problem solving. He was not particularly interested in creative design. But because he was so good, he was pushed by architects to do that, and he was one of the most important players in the British high-tech movement. So at some point, he started to worry that engineers were Iagos, Iago being the character in Othello. Iago is a saboteur. So the structural engineer is there to sabotage the architectural design. And he was struggling with that. He realized at some point that was not the right way to do things. He said, by using only pragmatism, we destroy the very basis upon which the good or noble things in our life exist. And I think that I believe in the Iago hypothesis. That's my dilemma. And I believe that we are, in a way, Iagos, and we have got to escape. And escape, he did. He did some of the most beautiful structures we have seen, and like I said, was behind the British high-tech movement. where the structure was the architecture. And he was a little bit of a rock star in the engineering world, if that's possible. I believe that we are witnessing right now a renewal in British architecture, but with a new material. This is a structure that we did about 10 years ago in Toronto. It's the Art Gallery of Ontario with Frank Gehry. You can see through the glass here that all the elements are at different angles. There are 2 layers of arches in front of the other, one for the main structure, the other one supporting the glass. And the angles for each element is different, which means that all the connections are different from each other. So we use CNC fabrication to fabricate pieces of wood that were all different, but try to keep all the steel elements the same. And this was the result. And I love this photo. We're in a museum, but people are not looking at the art, they're looking at the structure. Or maybe they're looking at the architecture, or maybe they're looking at both. Thank you.
Thank you very much, Eric. Thank you so much.
Thanks.